When we write the names and formulas of chemical compounds, we follow a set of rules set up and maintained by an organization of professional chemists all over the world. It's called the IUPAC, or IUPAC for short, the International Union of Pure and Applied Chemistry. This organization not only determines what rules we have to follow in working with chemical compounds, but also oversees the periodic table of the elements and determines when a new element can be added. IUPAC is respected by scientists all over the world, and we will use many of their resources this semester as we learn more about the elements and how their interactions impact the world around us. The basic idea behind the rules of naming and formula writing is this. The way you name a substance is based on what it's made of. So we need to spend some time looking at the periodic table in order to understand how the elements control the substances they make up. But first, let's make sure we're clear on what a chemical formula is and what it means. Here's a familiar substance, H2O. In our daily lives, we call this water. But according to IUPAC, this is dihydrogen monoxide. Why would chemists want to use such a complicated name when we could just call it water? Well, everyone around the world doesn't call H2O by the same name. For instance,
water,
Wasser,
水
水
Pani
Vody,
Água
water.
with so many languages and so many perspectives across the globe, scientists need a way to communicate across languages and cultural barriers. The IUPAC system is an international system that all scientists around the world use, so that chemists in Beijing and Buenos Aires and New York can all speak the same scientific language. So, dihydrogen monoxide it is. There are some important details you need to know in order to understand how to use the names and formulas we'll be writing. So let's look a little deeper. The letters in the chemical formula represent the elements that make up that substance. These letters come from the elemental symbols on the periodic table, and they tell us what kinds of atoms are in the substance. Each new element starts with a capital letter. Here we see that the capital H stands for hydrogen and the O for oxygen. The little numbers at the bottom of the formula are called subscripts. They tell us how many of each type of atom is present. If there isn't a number written after an element, we can assume a 1, but we never actually write the ones in chemical formulas. So this formula is telling us that there are 2 hydrogen atoms and 1 oxygen atom in every H2O molecule. As we've said, the chemical names come from IUPAC rules that all chemists around the world use to identify the substances they study. The big idea here is that names are always based on what the substance is made of. And then we have our common names. These are the everyday names we use to talk about substances that are common outside of the chemistry lab in our daily lives. Many of these everyday substances have unique chemical names that are very different from their commonly used names. For example, baking soda is actually called sodium bicarbonate because it's made of sodium, hydrogen, carbon, and oxygen. And vinegar is actually acetic acid. It's made of hydrogen, carbon, and oxygen atoms bonded together in a special arrangement that gives it the flavor we use in household cooking. Once we understand why we use special rules for naming compounds and writing their formulas, and we know how to use those formulas, we can start learning to actually name substances for ourselves. But we're going to need some help from the periodic table. To make this a little clearer, I've broken the periodic table into 3 sections. We can use these sections to better understand how the rules for naming and formula writing actually work. I call the first section the blue elements. These mainly include the elements in groups 1A and 2A. These are called the representative metals because they always react the same way in every. Notice that there are a few blue elements way out there in the middle of the transition elements. These 4 elements, aluminum, zinc, cadmium, and silver, are transition metals that act like representative metals, so they get to be blue. The second section is made of the rest of the transition metals, and they are the green elements. Since these metals do not always act the same way, they have their own special set of rules using the Roman numerals. We'll learn more about the green elements later. And then the last group is the red elements. The red elements include all of the nonmetals. Since they are all nonmetals, they all react in similar ways, so it's easy to group them together. But we need more than just some color-coded elements to understand the IUPAC rules. When these groups of elements interact in different combinations, they require a specific set of rules. So here are 3 categories that will help you know when to use which rules. Category 1 rules are for compounds made of blue and red elements. Category 2 rules are for compounds made of green and red elements. And Category 3 rules are for compounds made of all nonmetals, 2 red elements. If you use this system in categorizing the compounds we work with, you'll always know which set of rules to use, Category 1, Category 2, or Category 3. Try some examples. Use your periodic table to determine which category each of these chemical compounds fits into. Remember, it's all about what they're made of. So figure out what 2 elements make up the compound, find them on the periodic table, and then categorize it based on blue and red, green and red, or red and red. Pause the video to give yourself some time to work. I'll show you the answers in a moment. Here are the answers. How did you do? Still have some questions? Try watching the first part of this video a second time to see if you missed something important. Move on when you're ready for more information. There's one more detail we need before we can actually start working with chemical formulas and names. On the periodic table, there are these important numbers called charges. You might also come across the name oxidation numbers, but as far as we're concerned, we're just going to use the term charges. Many elements, the blue and the red ones at least, have their own special charge that they always keep. This means that when they bond or form compounds with other elements, they are always going to take on that special charge. So hydrogen always takes on a charge of +1, and oxygen always takes on a charge of -2. Notice that those extra blue elements way out there in the middle have special charges too. Aluminum always has a charge of +3. Zinc and cadmium are always +2, and silver is always +1. One really important pattern to pay attention to is the fact that metals always have a positive charge and nonmetals always have a negative charge. This is part of the definition of being a metal or a nonmetal. Metals are always positive, they give away their electrons, and nonmetals are always negative. They take on extra electrons. But take a look at all those green elements out there in the middle. None of them have a charge. How are we supposed to know how they interact with other elements when they bond to make new compounds? Well, the transition metals always have a charge, it just changes from situation to situation. So, based on what other element they are bonding with, the green elements might have different charges from time to time, sometimes +1, other times +2. What we do know is that they will always have a positive charge because they're metals. So part of the special rules for green elements and category 2 compounds is that we have to use a Roman numeral in their name in order to communicate what the charge on the metal is. We'll look more into that later. For now, just know that we will eventually have to deal with those complicated green elements. So that's it. That's all the important background information you need to know in order to start learning to write chemical formulas and name compounds in chemistry. The best strategy for learning this skill is to practice all the time. This is not a skill you can afford to be bad at. We will use naming and formula writing every day from now until the end of chemistry. So invest your time and energy now to make sure you'll be good at this in the long run. Good luck.